Yeah, we should be live at some stage. We should be live. Yeah, I have a bunch of new simulations and things for you. Yeah, I can hear myself as well, so I'll talk to myself, then we'll talk to the robot, and then we do a summary by Notebook LM. So let two robots talk to one another with everything we have done so far. So what's our usual spiel? Let's go check out BioniChaos.com. Everything we do on this channel is eventually available on this website. The last tools, yeah, we have this AI comparison, so this essentially comparison between generative and deterministic AI. So you have generative architecture, self-learning, probabilistic sampling, and then we have deterministic, that is rule-based. So for a set input parameters, you have the same results all the time. So in each industry, you can use both. Yeah, generative metrics, deterministic metrics, accuracy, precision. Generative is all human evaluation, perplexity. And this is the general strengths and risks chart, so you can see that they kind of complement one another. One is more reliable, transparent, faster. The generative models are more creative, scalable, flexible, a bit slower, and yes, less transparent. Well, because they were trained, and then you don't necessarily know what exactly they are doing, and they're not reliable. They can hallucinate quite a bit. So you have this compromise. So go check out. I'll pop this in the link to this into the chat. But if you have any feedback, we're more than happy to receive feedback on this, because we'll be developing more of this simulation tools, similar type of. Was I talking enough? Now we probably can keep going. Where's my live stream? Go live. Yeah, no one is there. It's okay, it's fine. Yeah, keep saying it multiple times, but it's interesting how when I actually use a robot, get more views. But that's mainly, yeah, so I was kind of, yeah, so you, by watching this, you're essentially participating in a behavioral study, because then we can use all the YouTube analytics of who is watching what to see. Yeah, we could publish it eventually. The 2.5 years of study, behavioral study on YouTube. What's interesting, what's not working. But yeah, so far we did, I think we have got enough results to tell that when I'm turning my microphone, start talking, the views actually dropping, engagement is dropping. When a Notebook LM, so two robots are talking, engagement is kind of higher. I think it's significantly higher. But then question is what happening when you have me talking to a bot. So let's actually try this out. Before we had this problem with that, yes, with using AI Studio, a Gemini 2.5 Flash experimental native. Yeah, that should be fine. Can reduce the number of tokens, 66 tokens per image. Should suffice. Let's use a different. A different voice for a change. Give it this screen so I'll have someone to talk to. If there's a human, by the way, yeah, go for it. Just pop your question, comment in the chat. Okay, what do you see on the screen real quick?
I see a web page with the title Strengths and Risks. It shows two radar charts comparing the strengths and risks of deterministic and generative models. The charts display ratings for things like reliability, transparency, and creativity.
And can you comment how accurate this is, or are there any problems with the chart?
The charts provide a visual comparison based on the data displayed. However, without knowing the specific criteria and data sources used to create these ratings, it's difficult to assess their absolute accuracy. They represent a particular evaluation model.
Okay, so what do you mean? Are they accurate or not?
The charts are accurate within the context of the evaluation model they represent. They visually show the relative strengths and risks as assessed within that framework. However, without knowing the specific criteria and data used to generate these ratings, it's difficult to judge their accuracy in absolute terms. They are comparative ratings within this specific model.
Okay, this is the overall topic. Can you sum this up real quick? And if you have any critical question or comment to the creator of this.
Okay, the overall topic is comparing the fundamental differences between deterministic and generative artificial intelligence models, focusing on their predictability versus creativity. The page highlights their core concepts and presents a comparative analysis of their strengths and risks. A critical question could be how the specific criteria used for the charts were defined and measured, and what data sources were utilized. Also, clarifying the nuances between the two types and potential hybrid models could enhance the understanding.
Okay, can you actually be more? They talk more casually, like normal words. I think you're like a data scientist slash stand-up comedians, and you are expert in this kind of stuff. So can you overview this page or what you currently see on the screen?
All right, buckle up.
Yeah, keep going.
All right, getting into the nerdy stuff. So this part here, core concepts, is basically the AI version of a personality test. On one side, we've got the logic of certainty. Think of it like the super rule follower. Totally predictable, everything's black and white, like a really detailed instruction manual. You know what you're going to get with this guy. Then over here, you've got the art of creation. This is the AI that gets fancy, creative, the unpredictable artist friend. It turns out new stuff, but you can't always peek inside its brain to see how it does it. That's the black box part. Basically, one's super predictable and transparent, the other's all creative and a bit of a mystery. Pretty cool way to think about the differences, right?
Okay, how about this page? Can you give me just one sentence and one question?
All right, check this out.
Yeah, keep going.
Okay, so this page is like the blueprint for how those two different kinds of AI actually operate. showing you the parts that make the predictable one tick versus the creative one. So, what's the real difference maker between their internal wiring that makes one so reliable and the other so good at making new stuff?
Okay, so they're different, totally different models, are they?
Totally. It's like they have completely different brains still built from the ground up. One's all about the strict rules and logic, like a super organized accountant. The other is more like a wild creative genius with a neural network doing its thing to whip up new stuff. Night and day, you know?
Okay, can you talk about this? Focus on the healthcare applications.
All right, let's talk healthcare. This part of the page is like the AI resume, showing where these digital brains strut their stuff. So when it comes to healthcare, you've got the super reliable, rule-following AI helping make clinical decisions like a seasoned pro, making sure everything's by the book. Then you've got the creative one, acting like a scientific genius, discovering new treatments and personalizing care like a mad scientist with a lab coat. It's like you've got the ultimate tag team of AI, one keeping things safe and sound, the others pushing the boundaries of medicine.
Well, it's actually not quite clear which one is which. So I assume, wait a sec, right. So in black we have the deterministic architecture, and then whatever red, orange, we have the generative AI. So considering, so would one be more like an engineer and the other one will be more like what in biomedical field?
Right on, exactly. So think of it like this. The deterministic architecture, with its rules and logic, that's like the super precise medical engineer, the one who designs the perfectly calibrated diagnostic machines or creates the fail-proof surgical procedures. Then the generative architecture, with its creativity and neural networks, that's like the brilliant drug discoverer or the geneticist figuring out crazy new therapies, the one who's coming up with totally novel solutions. They both play a huge role, just in completely different ways.
Oh, how about the clinician? Because clinician, is clinician a scientist or like an engineer or not? Or is it the opinion or the doing, like making decision based on the knowledge and opinion? Can you have a quick overview on this and a question? Be critical and fun.
All right. Let's talk about the real MVPs in healthcare, the clinicians. So, are they more like engineers following strict rules or scientists creatively diagnosing and treating stuff? Honestly, they're like the ultimate hybrid. They've got the engineer's mind for the rule book, the protocols, all the evidence-based stuff that keeps things safe. But then they've got that scientist brain, the one that can think outside the box, use their experience to connect the dots for weird cases, and make those judgment calls that save the day. It's like they're constantly blending the reliable with the innovative. So here's the million-dollar question. Can we build AI that nails that perfect balance between rock-solid knowledge? Right. So the Exactly. So the big challenge, the one that keeps the AI wizards up at night, is how to build an AI system that can be super reliable and follow all the strict rules while also being smart and adaptable enough to handle those crazy curveballs clinicians deal with. It's like trying to create a robot that can perfectly follow a recipe, but also improvise and come up with a Michelin star-worthy dish when the kitchen's throwing unexpected stuff at you. Can they build an AI that's both super precise and a brilliant problem solver, kind of like the best clinicians? That's the million-dollar question.
Yeah, it's getting all nonsensical. Let's do something else. Let's actually do something more practical. So we have this simulation. Okay, it doesn't really fit the screen. Doesn't fit the screen. Okay, let's go back to the 258 tokens per image. Okay, let's do this. Let Gemini adapt its response style to the input expression and tone. Okay, what do you see on the screen real quick?
I see a simulation called Magnetic Playground. There are 2 bar magnets on the screen with magnetic field lines shown around them. Below the magnets, there are controls to change their strength, flip their polarity, or remove them, and buttons to add more magnets, reset, or toggle the field lines.
Okay, I can't actually scroll. Hey, I can't scroll the page. So how would you improve the overall layout of the page and how it loads up? Mainly, I'm also concerned about the lines, the toggle field lines. Do the lines seem correct to you?
Improving the layout and loading time could definitely make the experience better. For the field lines, they should typically flow from the North Pole to the South Pole, indicating the direction of the magnetic field. If they appear different than expected, there might be an issue with the simulation. What do you observe about the lines right now?
Hey, can you have a look at the lines? Can you see the lines?
Yes, I can see the field lines clearly. They are shown as lines extending from the magnets, illustrating the magnetic field around them. They look like they are flowing from the North Pole to the South Pole, as expected.
But is there anything weird with the lines as far as you can tell?
Based on what I see, the field lines appear correct. They are shown originating from the North Poles and curving towards the South Poles, which is the standard representation of magnetic fields. If there was something unusual, it might suggest a problem with the simulation.
Okay, now when the field lines overlap, in this case currently visible on the screen, should the two magnets attract one another already? Because currently I have to bring them really close for them to actually start moving towards one another. Can you explain what's going on?
Even when the field lines overlap, the strength of the magnetic force decreases significantly with distance. It's possible that the default strength of the magnets in the simulation is set low, requiring them to be very close for the force to be strong enough to cause noticeable movement. You might try increasing the strength of the magnets to see if they attract sooner.
So currently with this simulation, as you can see with the settings, the strength of each magnet is at its maximum. What would you do? Would you increase the scale for the strength adjustment or not?
If the magnets are already at maximum strength and still require close proximity to interact, increasing the scale for the strength adjustment could be beneficial. This would allow you to simulate even stronger magnets, potentially increasing the distance at which they attract each other. It's like extending the range of the strength control.
Okay, and what else would you improve about this simulation?
Perhaps adding a visual representation of the force acting on each magnet could be helpful. This could be shown as arrows indicating the direction and strength of the attraction or repulsion. Also, making the field lines visually richer, perhaps changing their thickness or color based on field strength, might provide more information at a glance. Additionally, allowing users to directly adjust the orientation of the magnets could offer more control and flexibility.
No, so we can align the orientation and everything, as you can see here. So that should be fine, isn't it?
Yes, aligning the magnets so that their opposite poles are facing each other should result in strongest attraction. The magnetic field lines flowing from the North Pole to the South Pole should connect, pulling the magnets together. It sounds like you've positioned them correctly for attraction.
No, but based on our discussion and what you can see on the window, how would you improve this simulation?
Based on what I see and our
Yeah, keep going.
Right. To improve the simulation, I would suggest incorporating visual cues for the magnetic force, like arrows indicating force strength and direction. Enhancing the field lines to reflect strength through thickness or color would also add clarity. Additionally, providing controls for direct magnet orientation adjustments could improve user interaction and make the simulation more informative and engaging.
Okay, so we adding visual force arrow, so each magnet will now display an arrow indicating the direction and magnitude of the net force being planted by the other magnets. So does that sound legit? Okay, obviously if you have 3 magnets, the forces are greater. You get a lot more stuff happening, which is a bit of chaos.
It sounds like the force arrows are providing a clearer view of the interactions. It's natural for the dynamics to become more complex with multiple magnets, as each magnet exerts a force on the others. You can explore how different arrangements and strengths affect the overall's behavior.
Again, how about adding different types of magnets?
That's an excellent idea. Introducing different types of magnets, like spar magnets, horseshoe magnets, or even circular magnets, would enhance the simulation's educational value. Each type has unique magnetic fields, and allowing users to experiment with their interactions would provide a richer understanding of magnetism.
Okay, we have this developer that is making the code for us, but I think it stuffed something up.
I understand your concern about.
Yeah, do you also know, like, the developers always defaulting to using Tailwind, CSS, and Google APIs. Do we have to use those or not?
Whether you need to use Tailwind CSS or Google APIs depends on your project's specific requirements and the decisions made by your team. If using those technologies is part of the project plan or necessary for certain features, then yes, they might be required. It would be.
Yeah, if you're just prototyping, would you use those or not?
If you're just prototyping, you might not necessarily need to use those specific technologies right away. Prototyping often focuses on exploring the core concepts and interactions quickly, so simpler tools might be sufficient for initial exploration. However, if using those technologies is crucial for demonstrating specific features, then they might be included in the prototype. It would be best to clarify that with the developer or your project requirements.
Yeah, we have the developer broke the code for us. The fields are not visible at the moment, and I can't control things with the mouse. Can you explain? Can you rewrite it into instructions for the developer of, what needs to be changed and improved?
Okay, I understand the magnetic fields are not visible and the mouse controls.
Yeah, keep going.
Right. I can provide instructions for the developer to address those issues. The instructions could include ensuring the magnetic fields are correctly rendered and restoring the functionality for mouse control. This should help make the prototype interactive and visually accurate. Would you like me to provide those instructions in more detail?
Let's see. Let's just provide the general thing for the developer. I'll see what's happening. What is happening? Okay, while the developer is doing the job, can you tell any funny jokes or something about this web application? We are live streaming on the whole development process on YouTube, by the way, and eventually all the tools we make are available on this website. Any funny comments on that? Oops, I think we lost. Yeah, so while the developer is doing what they're doing, can you give a quick comment on what's wrong with this web application potentially? How can it be much improved by a lot? And also mention, so we're live streaming at the moment. If you have any funny comments, that you can go for it directly, first person. But also everything we do is available on this website. What do you think of that?
Well, it sounds like the magnetic fields are playing hide and seek, and the mouse is on a coffee break. For the developer, the key things to fix are making those field lines visible again and getting the mouse controls working properly for dragging the magnets. It'll make the whole experience much more engaging. And since you're live streaming this, it's like having a live debugging session with an audience. Maybe your viewers can even suggest some cool new features to add. And for everyone watching, be sure to check out their website for more interesting interactive tools. With these fixes, it's gonna be a fantastic prototype.
Okay, so the developer fixed some stuff. We'll actually have the code. We will have the code as a copy. No, we'll keep this one as a copy and we'll update to what Gemini have made. Sorry, should be made clearer. Okay, so that's what we've got. So I need to scale this thing so it suits the screen much better. Yeah, so now they attract, repel. Okay, that can you see any changes and what was changed? We have those arrows for the forces of the two magnets. Can adjust the strength manually. Can flip, so now they should start attract each other. We can flip again, they should detract. So that's kind of nice. We can control orientation both. Ooh, okay, a lot of forces. Oh, wait. Yeah, but the problem is, does the show field lines or toggling the field lines? Does it seem to do anything? What do you think? As opposed to what we had before, what do you reckon?
So you're asking if the changes made now allow you to see the field lines more clearly or interact with them differently compared to before the fixes?
No. So can you address the developer directly and explain what on earth is wrong with this web application and and ask the developer why did we stop seeing the magnetic field lines? Can you do that for me?
It seems like the magnetic field lines are no longer visible in the simulation after the recent updates. Could you please explain why the field lines stopped appearing? The user is wondering what caused this change and would like to see them again.
Okay, that's actually pretty good. I like a bit of attitude in your question. Any other problems with this web application as far as you can tell? I'm thinking the layout of the screen.
Regarding the layout, are you noticing any issues with the arrangement of elements or the overall design that could be improved?
Okay, that's pretty good. If you can give more attitude to the developer, that would be great. So any other problems?
Certainly. It seems there are some issues with the layout and the visibility of the field lines. The user would appreciate feedback on improving the overall design and ensuring the field lines are displayed correctly.
Okay, any other issues, any other problems with this web app?
The main issues identified are the inability to see the magnetic field lines and potential improvements to the web application's layout. Are there any other concerns you'd like to mention?
Okay, moving forward, while they actually updating the code. They're still updating the code. It takes them quite a while. They're a bit slow. The developer is a bit slow. Do you have any other suggestions as to how this web application can be improved? I'm thinking adding an addition of different types of magnets. What do you think of that? Any other issues with the web application as far as you can tell?
So, just to confirm, the main issues are the visibility of the magnetic field lines and potential improvements to the web application's layout. Is there anything else affecting the user experience?
I think, okay, it's actually the developer actually brought back the field lines, but they're super faint. I can barely see them. Can you grill the developer on this?
I understand. It seems the field lines are back, but they are very faint. Could you please address the developer and ask why the field lines are not clearly visible now? The user would appreciate better visibility.
Okay, don't mind you two hurting the developer's feelings, considering the developer is another AI.
It seems the magnetic field lines are now visible, but they are quite faint and difficult to see clearly. It would greatly improve the user experience if these lines could be made more visible. Could the developer please adjust the visibility of the field lines?
Yeah, the developer is still working on it. Can you mention why do you think it's a good idea to publish everything open source on this website? Can you provide your thoughts?
That's an excellent question. Publishing everything open source can be very beneficial for this website. It promotes transparency and collaboration within the research and education community. Others can review the code, suggest improvements, or adapt the simulations for their own purposes, which can lead to faster innovation and a more robust platform. It also builds trust with users by allowing them to understand how the simulations work.
Okay, so we have the updated version of the simulation. I don't know, can you even see the magnetic field lines, or is it only me? I'm not able to actually see them. What happens if I increase the strength of the magnet? Yes, I can see them a bit better, but they're not great. And they're doing something weird as well. So yeah, we need to fix we need to go back. They were better before. We need to fix the magnetic field lines, make them clearer, longer, more accurate, and so we can actually see them. Yeah, they should go all the way from the north to the south pole of the magnet. Can you explain on that? All that? You can address the developer directly if you like.
I understand. Addressing the developer directly, the user has pointed out that the magnetic field lines, while now visible, are very faint and not displaying accurately. They recall the field lines being clearer in a previous version. It would significantly enhance the user experience if the visibility of the field lines could be improved, making them clearer and ensuring they are displayed correctly, extending from the North to the South Pole as expected.
By the way, if you are familiar with any publicly available models, to fix this issue, as you can see it right now, which model would you use? A Gemini, Claude, or ChatGPT?
Given the visual and interactive nature of the magnetic playground, a model like Gemini, which is strong in multimodal understanding and reasoning about complex interactions, might be well suited for identifying and suggesting fixes for the issue. Its ability to analyze visual dynamics could be quite helpful.
Okay, that's exactly who the developer is. It's Gemini 2.5 Pro, but it seems like they having a bit of trouble. What do you think?
It sounds like they might be encountering some specific challenges with that particular simulation. Sometimes, even advanced models can require specific tuning or adjustments to work perfectly in complex interactive environments. It's part of the development process.
Yeah, I have another not related question for you. No, wait a sec.
Okay.
Yeah, so we improved no, we stick to the web application. Sorry.
All
Alrighty. Wait a sec. Yeah, so they still having trouble. Yeah, it's a bit better, but not much. Based on what we discussed before, yeah, the field lines. How would you improve the field lines? Need to probably redo that part of the code or something. Yeah, if you don't mind, I don't mind you giving attitude to the developer if you like, considering it's another AI.
Based on physics principles, improving the field lines could involve making them smoother and more accurately represent the magnetic field strength by varying their density. Also, ensuring they dynamically adjust correctly with magnet movements would enhance the simulation's accuracy. It's important for them to provide clear directional information.
Uh, okay, and do you think the developer needs to redo that part of the code, or do you think they will be able to fix it from where we are at the moment?
It really depends on the underlying code for the field lines. If the core logic is mostly correct, perhaps some fine-tuning of the rendering parameters or dynamic adjustments could fix it. However, if the fundamental calculations or update mechanisms are significantly flawed, they might need to revisit that part of the code more extensively.
Yeah, they're still developing the code. Do you have any funny comments in the meantime? By the way, so we're live streaming on YouTube. What do you think the viewer should do in terms of, what they see on the screen? What do you see on the YouTube screen normally as a viewer, and what buttons should you press?
It sounds like the developers are having some magnetic challenges themselves. Maybe they need to align their code's polarity properly.
YouTube screen normally as a viewer, and what buttons should you press? Okay, let's close this for a sec because that window already got to, the chat with Gemini already got to a whopping 4.7 gigabytes. So that's not good, is it? That's not fun. So currently we're having this weird thing. Let's actually try and fix the code with let's do Claude. Let's give Gemini a break. Let's actually do Claude Sonnet 3.7 thinking. Okay, we need to improve. Hey, can we find any issues with the magnetic field lines? And what do we need to do to actually improve them? Currently, they seem to be too short. So when the magnet is there by itself, should it go? Okay, it wouldn't let me finish.
Magnetic field line improvements. I've analyzed the current field line implementation, and there are several issues causing the field lines to appear too short. Limited iteration count, 150 steps maximum. Fixed step size that doesn't adapt to field strength. Early termination near south poles. Field magnitude threshold might be too aggressive. Solution steps. Increase the maximum iterations per field line. Make the step size adaptive based on field strength.
Okay, so we got the point. That's Claude 3.7 thinking. So we started this simulation in Gemini 2.5 Pro. Kindly provided. Well, we are paying for this, but anyway, it did provide. We would have had to pay much more to a human developer. That's for sure. Okay, so it's actually updated stuff. Yeah, we will keep this for sure. However, they seem still to be very short. What model should we use? Just do regular 3.7, not the thinking model. Okay, so based on what we discussed before, it is a bit better, but the magnetic field lines are still a bit too short. Can we actually fix that? Find any relevant bits in the code and try and fix the lines? Okay, so sending it essentially.
Extending magnetic field lines. I'll make the field lines even longer and more visible by adjusting several key parameters in the field line generation code. The main issues are: field lines terminate too early because the step size and iteration count are still not optimal. 2. Field magnitude threshold may still be too aggressive. 3. We can improve the field calculation to better simulate real magnetic fields. Solution steps. Index.html. I'll improve the.
Okay, you can do it quietly. Not sure why it's reading the code. It's actually is better when I increase the strength. It looks more legit. Is it? Not sure. Yeah, we have the force. The yellow ones are force lines. So that's kind of nice. Yeah, we can make a total chaos out of it by adding another. Why aren't we able to scroll? Okay, now we're having a full-on chaos with 4 magnets on the screen. That was the bot, the agent. It restarted the thing for us. Restarted the thing. Okay, this is actually better. What we had originally. Okay, this is much better. That's a keeper. Claude 3.7. Thank you very much. Thank you very much. Something up with the slider. Hey, can we also check if there is anything wrong with the sliders? They seem to be discrete instead of continuous. Is it intentional? Like I'm able to click on them, but I'm not able to just move my mouse cursor while pressing the slider. Is this intentional?
I'll analyze the issue with the sliders in the magnetic simulation and provide a solution. Problem analysis, slider functionality. The sliders for magnet strength and orientation are indeed behaving in a discrete rather than continuous manner. The issue is that the event handlers are only set up for the input event, but there's no specific handling for mouse drag operations on the sliders.
Okay, that should be an easy fix, isn't it? Should be an easy fix. Thank you very much. And by the way, magnets are surely related to biomedical engineering and data science, so I can explain that. We'll actually have to add it to. Yeah, I wish the agent was a bit quicker. Well, I guess we can use a different model. We can use a quicker model. Currently it's Claude Sonnet 3.7. Okay, now we have this. Yeah, a lot of strength to the magnets. I don't see the where's the lines. No, I do see the lines. You can flip. Yeah, it looks pretty good to me. I don't know, are there any magnet experts watching this? We had this standard prompts for web applications. I don't know, are we ready? Well, we need a better model to tell us if we are ready for production. Do we? Let's do Claude Sonnet 4 for a sec. A new chat. We will just do, yeah, let's just do edit. We can do edit. Wait a sec. Add those prompts. We need those prompts. Let's actually make a copy of this real quick because we do like it a lot. Okay, we have this single page HTML, JSON, CSS only. Don't use React, TypeScript, Tailwind, Google APIs. Yeah, we don't. We don't mind them, but I don't think we need them at this stage. We want this to work with keyboard, mouse, and touch. Include audio with toggle option off by default. Wanted educational, interactive, and accurate, obviously. Well, nothing is obvious when you talk to a generative model, is there? Is it? A text web app overview, how to use future direction below the canvas. In this case, we want to include how magnets are relevant to biomedical engineering. Of course, they're relevant. Don't tell me they're not relevant. Don't know text scroll. Yep. Layout works on all screen sizes without overflowing. Oh, right. And for showcasing, yeah, we want, well, that's for educational purposes. Like when you load the page and you don't know what is it you're looking at, we'll have a play demo button that automatically cycles through all the predefined functions. So we have Claude Sonnet 4. Claude Sonnet 4. Give it the whole code. Turn this into a single page interactive simulation animation game. Claude Sonnet 4. Do we trust Claude Sonnet 4? Yes, we do. Oh, we should have run it in an agent, or currently we're trying a single shot. It wouldn't work, would it? Maybe not. Maybe. Well, even if it's not relevant to biomedical engineering / biomedical data science, at least we are learning how to use those these code generating models. Doesn't make sense calling them language models. They're more like, well, they are, well, currently we're using JavaScript, so what are they? JavaScript. What is still discrete? Yeah, the buttons are still discrete. Didn't we just change it before? I thought we did. Okay, eventually we will. So I'll finish up by writing the description for this thing. Hopefully Claude 4 doesn't actually break. Hopefully it doesn't break the code. If it's still working, we have the description at the bottom of the page as we requested. We will pop everything into Notebook LM. So hopefully it will actually make some sense. And also, when I'm talking, the views are going down. Yeah, 4 magnet chaos. What's the strength like? Should we just pop all the strength up to max? Yeah, now they're going. Yes. it's just gonna all get stuck, laid up on top of one another. Poof, poof. Yeah, chaos, magnet chaos. What's going on? Ah, maximum 4. What? I didn't program for that. Yeah, seem to cancel each other out. Okay, Claude Sonnet 4 is really not lazy. Keeps going, editing the code. Oh, okay. Change things, didn't we? Okay, the mouse still works. The fields look legit. We have an equation. Force between magnetic poles. Simplify. Okay. We have a demo. Head magnet. Head magnet. Head magnet. Only 4. I can only do 4. That's okay. Strength. Not the. Yeah, the. I can't scroll those. Flip. Very nice. Okay. So we removed, I take it. Okay, the code now is a whopping. It's more than 1,000 lines of code. Okay, we have the CSS and this and that. We want to change the strength. Or is it okay? I'm not sure. Shall we make them much stronger? Okay, let's do 3.7 because those requests should be pretty straightforward. Pretty straightforward. Ah, yeah, the screen. Yeah, I like the equation and everything. I think we are ready for a notebook LM to take over. Are we? I think we are. Oh, wait. Let's actually use Gemini 2.5 Pro for this. In the section below the canvas where we have the text, can we add a whole section, a text paragraph about how magnets are relevant to biomedical engineering and data science? So obviously the obvious aspect is how They are used in imaging, but potentially other applications as well.
Of course. I will add a new section discussing the relevance of magnetism to biomedical engineering and data science.
Okay, I can do it quietly. Because we later will give it to a better language voice model to read out. That is being notebook LM. What else do we have? We have an electromagnet interactive simulation. Yeah, we have how hair is growing. Yeah, might be less interesting. Might be less interesting. Okay, we have biomedical data science application feature enhancements. Yeah, we could have made that text. Should we add more to the text or not? Okay, maybe just keep it as is. Keep it as is. Okay, we're ready for notebook LM. I think we are ready. Any objections? No objections. So we add the code as text. The code has the text explanation down the bottom. And see how long it is. We will see how long it is. We will. It was discrete. Let's do 3.7. Can you also, we tried changing it before, but I think it didn't quite work. So with the scrollers, currently they are discrete. I cannot click on the scroller and just change the parameters. So this is both for strength scroller and angle scroller. Can we fix that somehow, or would it be too hard?
I'll fix the slider interaction issue where you can't directly click on a specific point of the slider to change the value. This is a common UX problem where input range elements only respond to dragging, not clicking at specific positions. Step-by-step solution. The issue is that the sliders are only responding to input events when dragging, but not properly handling clicks at specific positions. We'll add event listeners for the mouse down event on the sliders to
Wait, I think it's actually the other way around. Can you explain first and then change the code, update the code accordingly? It's the other way around. I'm able to click on it but not slide.
I'll first explain what's happening with the sliders, then make the necessary changes to fix the issue. Explanation of the issue. Currently, the sliders in the magnet controls have the opposite problem from what you initially described. You can click directly on the slider track to set.
Okay, can do it quietly because I don't like this this robotic voice. We don't want to hear that. Yeah, once you hear something like notebook alarm, you can't go back. Sorry, any other robot voice model? It's not happening. It is not happening. It is not. Okay, I actually like it a lot. you like it, you know what to do. Like, subscribe, unsubscribe, comment. Bad comments are welcome. we're currently not getting much comments to begin with, so even if you have something bad to say, you are welcome as well. Or not. We'll see. We'll see how we go. We will see how we go. 3.7. Respond direct clicks. Is it okay? The mouse is working. Okay, Claude Sonnet 3.7. Thank you very much. It's working really nice. Again, we have 10 minutes of Notebook LM. So if you don't like AI, this is your time to stop listening or watching, because the robots are coming. The robots are coming. So I'll do a 10-minute review of everything we've done of this web application. Brought to you by Google's Notebook LM.
Welcome back, everyone, to another deep dive. Today, we're jumping into something really fundamental, kind of invisible, actually, magnetism. And we're using this amazing interactive tool to help us get a handle on it, the magnetic playground simulation.
Yeah, so our plan today is, well, first, just touch on the basics. What is magnetism? Then we'll really get into how this simulation, this magnetic playground, makes these complex physics ideas feel, real, almost playful.
Yeah.
And then this is the really cool part. We'll see how it all connects to like biomedical engineering, data science, surprising stuff. Okay, let's unpack this.
Absolutely. And what's fascinating here is that understanding these invisible forces, it isn't just academic, right? It's really the foundation for so much of our modern tech. It's amazing how a, relatively simple simulation can shed light on principles behind things like MRIs or even data storage.
Exactly. So maybe let's start right there. What is magnetism fundamentally? I mean, we know it's one of those basic forces in nature. It comes from moving electric charges. And every magnet, it has the two poles, north and south.
That's right. And they create these invisible magnetic field lines stretching out into space.
Precisely. And those field lines aren't just conceptual. They represent a real force field. We even have a simplified formula for the force between two magnetic poles. F equals K times M divided by R squared. Basically, it tells you the force depends on the strength of the poles, the and ms, and crucially, it decreases really fast with distance, RCI. That's the inverse square law. Double the distance, quarter the force.
The inverse square law, that pops up everywhere in physics.
It really does. And another key point here is that magnetic fields are conservative, which essentially means energy isn't lost or gained overall in the system. It just changes form, like between potential and kinetic energy.
Okay, so we've got the inverse square law, energy conservation, and the really basic rules that I think most people remember. Opposite poles attract.
North pole, south.
And the poles repel.
North pushes north, south pushes south.
Yeah, simple rules, but they govern some pretty powerful interactions, don't they?
Absolutely, and that's where seeing it helps.
Right. Talking about invisible forces is one thing, but how do we really, get a feel for them? And this is where the magnetic playground simulation comes in. It's designed specifically to let you explore these forces, see them happening. It uses, real-time physics and field line visualization. So you actually watch the magnets move realistically. Here's where it gets really interesting.
It really is. The hands-on part is key. The source material explains how you use it. You just use your mouse or even touch. Drag the middle of a magnet to move it around the screen. Or if you drag near the edges, near the poles, you can rotate it.
Oh, neat. So you can position and orient them exactly how you want.
Exactly. And there are sliders, too, so you can adjust the strength of each magnet and its orientation precisely. Real-time updates. Plus keyboard controls for quick actions.
Like what?
Well, spacebar adds a new magnet. R resets the whole thing, clears the board. F is really useful. It toggles the field lines on and off so you can see them or hide them.
Ah, okay.
D starts and stops at demo mode, which is kind of cool to watch. And A toggles the audio if there are sound effects associated with the interaction.
And it shows the forces, too.
Yep, with force indicators, little yellow arrows on each magnet. They show you the direction and implicitly the strength of the net force acting on it.
Yeah.
It makes it all very, very tangible.
It's fantastic how a good interface makes complex physics so much more approachable. So this isn't just for playing around, though. It demonstrates specific physics concepts, right? You mentioned the field lines, visualizing direction and strength.
Exactly. And you see the inverse square law directly move a magnet away. Watch those force arrows shrink. It also shows superposition really well when you have multiple magnets.
Ah, right. Things get complicated.
Yeah, their fields just add up. The simulation calculates that combined field instantly, showing you these intricate patterns that emerge. It's not just one magnet influencing another, it's the whole system interacting.
That's a key concept.
Definitely. And conservation of energy, too. You can push magnets together, give them potential energy, let go, and watch them fly apart, converting it to kinetic energy.
Yeah.
You might oscillate for a bit.
Until they settle down, maybe due to some simulated friction or damping.
Right. And finally, torque and rotation. You can see how off-center forces make the magnets twist and turn to align themselves.
So you learn these core concepts by doing, essentially.
Precisely. And that leads naturally into trying out little experiments, like you could try to achieve magnetic levitation. It's tricky. You need to balance the attractive and repulsive forces just right.
I can imagine. That would be a fun challenge.
Or just watching carefully how those field lines behave. See how they stretch between opposite poles but curve away from poles. It reinforces the rules.
Testing the strength slider too, I suppose. See how a stronger magnet reaches out further.
Absolutely.
Yeah.
How does doubling the strength change the interaction distance? You can measure that, roughly. Or just throw 3 or 4 magnets in and see what happens. You get these really complex, sometimes beautiful equilibrium patterns.
Exploring the complexity.
Yeah. And watching the energy transfer during oscillations is quite insightful,
Right.
too. But, playing with this naturally makes you think. This raises an important question. How do these simple rules, these interactions we see in the simulation, actually apply in the real world, beyond the playground?
That's the perfect pivot, because it's easy to think of this as just, physics homework or a cool visualization. But these principles, the very things the simulation shows us, attraction, repulsion, fields, forces, they're absolutely foundational to some major modern technologies.
Yeah.
You mentioned biomedical engineering and data science. So what does this all mean? How does it connect?
Well, the connection is incredibly direct and impactful. Let's take biomedical first. The huge one is MRI magnetic resonance imaging. It uses incredibly powerful magnetic fields, far stronger than these little simulated magnets, along with radio waves. But the fundamental principle is manipulating magnetic properties, this time of atomic nuclei in your body, mostly hydrogen in water, to create unbelievably detailed images of your organs, tissues, brain, everything.
It's about cutting you open. It's revolutionary.
It truly is. And it all stems from understanding and controlling magnetic fields. Beyond imaging, there's cutting-edge research using magnetic nanoparticles, tiny, tiny magnets,
Nanoparticles for what?
for things like targeted drug delivery. The idea is you attach drugs to these magnetic nanoparticles, inject them, and then use external magnetic fields to guide them precisely to, say, a tumor.
Wow, so you could deliver chemo right to the cancer cells and minimize side effects.
That's the goal. It's still largely experimental, but the potential is enormous, based on the same fundamental magnetic principles.
Okay, that's biomedical. What about data science? That seems like a bigger leap.
Maybe less obvious, but definitely connected. Think about those MRI machines again. They don't just produce pictures. They produce vast amounts of digital data representing the magnetic signals they detect.
Right, huge data set.
Exactly. And analyzing that data is a massive task for data science and machine learning. Algorithms are trained on thousands of MRI scans to automatically detect subtle anomalies, maybe early signs of disease that a human eye might miss.
So AI reading the scans.
In a way, yes, or assisting the radiologist. They can also be used to predict how a disease might progress, or even to improve the quality of the images themselves, maybe making scans faster or clearer.
So turning that complex magnetic field data
Into life-saving clinical insights. That's the essence of it. And interestingly, even this relatively simple magnetic playground simulation, it models complex system interactions, right? Multiple magnets influencing each other dynamically. That kind of system thinking is exactly what data scientists do, trying to understand and predict behavior in complex systems, whether it's magnetic fields or, customer behavior or climate patterns.
That's a really powerful connection. From a simple virtual magnet interaction to predicting disease from complex data. And the simulation itself isn't standing still, is it? The source mentioned potential future enhancements. Things like different magnet shapes, not just these simple dipoles, but maybe circles, horseshoes, bars,
Yeah, that would add another layer of realism.
and adding magnetic materials like simulated iron filings that would physically line up with the field lines.
Oh, that would be visually fantastic for understanding field shapes.
Or electromagnetic coils, showing how electric currents create magnetic fields.
Bringing electromagnetism fully into it, that's a big step.
Maybe 3D visualization, measurement tools like a virtual Gauss meter to read field strength.
Make him more quantitative.
Even historical examples, or including the Earth's magnetic field. Lots of possibilities.
It really shows the potential. And if we connect this to the bigger picture, it just highlights how these tools, these simulations and visualizations, are becoming so important for learning and discovery. By making complex physics intuitive and interactive, they accelerate our understanding. And that understanding fuels innovation across so many fields.
It really drives home the point, doesn't it? We went from these invisible forces, these simple north and south poles attracting and repelling in a simulation, all the way and understanding technologies like MRI that see inside the human body and data science techniques that help save lives. It's quite a journey, starting from visualizing the invisible with a tool like the magnetic playground.
It absolutely is. It makes you appreciate how fundamental these forces are and how powerful visualization can be for grasping complexity. Kind of makes you wonder what other invisible forces or complex interactions are shaping our world that we just haven't found the right way to see yet. Thinking about everything we've discussed, from the basic physics to the advanced applications. What stands out to YU as the most surprising connection or idea from this deep dive?
Yeah, that was Notebook LM. So we just did this simulation earlier and then turned it into this code. I really like the user interface and everything. We had the prototype made by Gemini 2.5 Pro, and then we finished with Claude, both Sonnet 4, 3.7 thinking, and just 3.7 to fine tune the code, essentially make it ready for production, because everything we do is available on BioniChaos.com. Go check it out. Let us know what you think. This Fourier transform visualization. So don't forget that meant to be a like. And with 25 vectors, it's actually repeating the drawing we made. Again, 25 will be able to make it, or do we need more vectors? It's doing fine. Can slow it down, zoom onto where it's currently drawing. Yeah, you can see all the vectors. So there are 25 of these lines. They calculate it essentially real time, which is pretty amazing. We're calculating all the vector length, and they're just rotating around one another. I can speed it up again So yeah, like, subscribe, and tell your friends. Check out the page. Check out the page. And we might finish it here unless unless magnet simulation is a whopping over 1,000 lines of code. Just need to make it ready for production. I will need a thumbnail image. Thumbnail image. Yeah, better do it now, because later I might forget. The image is called thumbnail. Index HTML. If you have any questions, this is a good time. Even if you're watching it not live, I can still answer your questions. Yeah, it's just 3 things we need to change before the tool is ready for production. Do you want me to sing or something? Probably not. Probably not. So we're releasing two tools. It's that HRF dataset from yesterday. It's the high resolution fundus imaging. So yes, we took the dataset, but we did change the way we show. We display the data. We also wrote Python code to actually transfer the data from these weird diff files to a more web-friendly files. So hopefully that helps. Hopefully that helps. Okay, so we're adding the magnets. To the landing page. Yeah, this is the boring bit, isn't it? Deploying stuff. Well, it should be really fun while it's deployed. Because we like deploying stuff. Yeah, so that's currently in currently running on a local server. Yeah, there's some weird thing that we can sort out later. This is a minor bug. What is it? We should be having major, minor, and we already covered it in the YouTube video. We had the notebook LM chatting about it. So that should be good. That should be good. It should be good. Let's deploy. Deploy. You might be asking, why am I doing this live? The main reason is that later I might forget. Well, there are probably other reasons as well that I haven't thought of yet. Okay, I think we deployed. Right, we have these two new tools. Let's close that and check if they are working. Yeah, seem to work very well. You have this keyboard shortcuts, adding more magnets. As the robot explained before, can increase the strength of each magnet and see how they interact. You have all this description. We used to put this notebook LM description on the page. Well, now they'll just be on YouTube. Hope you don't mind. Hope you don't mind. And that's the other one. Yeah, it says this lazy loading. Yeah, eventually it's loading. Hopefully it's loading from the CDN. Can close this. You have shortcuts. You need to remember this shortcuts, keyboard shortcuts. 1, 2. 1 and 2. Yes, so 2 is toggling the vessel overlay for your convenience. For your convenience. And 1 is toggling that mask. The mask is just making it like very up. You can actually see it better, but if you remove the mask, you can actually see. You can actually see the original image. And the overlay vessel overlay is semi-transparent. Okay. And this semi-transparent vessel overlay was actually drawn by hand. Amazing that someone actually did it. Thank you very much. You have this diabetic retinopathy, where you have this extra vascularization, I think it's called. So yeah, so they were labeled. It's a great data set. Where someone did the vessel overlay by hand. Quite amazing. There's not many images though, but yeah, still quite a skill, quite a task. So thank you very much. Yeah, that's where the original dataset is. I think. Is that link? Yeah, website. Yeah, new website. Well, anyway, it's somewhere on that website. To go find the original link. And yes, you can actually review the data, review this data set. So yeah. And we have this new magnetic simulation thing going on as well for you. Hey, go check it out. Let us know what you think. Don't forget to like, subscribe, unsubscribe. You know what to do.